All right, so today's lesson is continuing quadratic functions. We're going to learn a new method for solving a quadratic equation. And we've actually started this already in the last class when we solved by using square roots, by completing the square. We did this already to an extent. So we're just going to like add an extra process to that. So continuing our learning about how to solve quadratic equations. All right, so excuse me. So last class we learned, so far we've learned several ways to solve quadratic equations. It's not always possible to use the zero product property, especially if the equation is difficult or even impossible to factor. So just to make a note on this, zero product property is when we take an equation in standard form. So you can see like down below, here's our standard form down here in the box. When we take an equation in standard form and we factor it, if we're able to, so we factor it and then we set each factor equal to 0. That is what we mean by using the zero product property. So we have a standard form equation set equal to 0, and then we factor it and set each factor equal to 0. So that's one of the processes we've learned. But sometimes we're not able to factor. So then we learned about solving equations in perfect square form. So this is another approach. And see, this equation here is an example of perfect square form, or down here in the second box, here's our perfect square form. We have an expression squared equal to some number. And when we solve perfect square form equations, what we do generally is we take the square root of both sides of the equation, so square root, to get rid of the exponent and then be able to isolate our x. And that's what we learned last class. So these two methods are so far what we've learned. Sometimes we can't factor. And so, we'd like to take the square root. But if our equation isn't in perfect square form, then, we would get kind of stuck. So it can be helpful sometimes to change a quadratic function from standard form to perfect square form in order to be able to take the square root of both sides and solve it that way. If we're not able to factor, another way we could approach solving is by just changing the format of the equation in order to use this other method, square roots. And that change from one form to the other is what we call completing the square. So when we, again, transition from standard form to perfect square form, we are completing the square. And that helps us to then finish the solving using square roots. So our essential question today is, how do you solve quadratic equations by completing the square? All right, so in this problem, what we're going to do, did I go too far? Yes, I did. In this problem, what we're going to do is we are going to be comparing perfect square form and standard form. And in order to do that, we're going to start with a perfect square form equation and we're going to rewrite it in standard form. So basically, we are going to we're going to go from perfect square form to standard form. This is sort of our job today in this problem. So in order to do that, what I need to do is I need to multiply out this expression here. I need to multiply out x plus 2 squared. And I want you to be very, very careful. When you square an expression like this, you don't distribute the exponent. That would be incorrect. Remember, when you square something, it means to multiply it by itself. So technically, x plus 2 squared is the same as this. It's the same as this. So this is really what we have. X plus 2 times x plus 2 equals 3. So we need to multiply out this x plus 2 times x plus 2. And I think one of the best ways to do that is to use an area model. So what I'm going to do is build myself a square and start filling in the details of my expression. So I have x plus 2 times x plus 2. So I'm going to do an x plus 2 on this side and also an x plus 2 on this side. And just to be clear, this 3 right here is a random number. This number could be anything. The perfect square form is always some expression squared equal to a number. Sometimes that number is 0, sometimes that number is not 0. In this case, it's a 3. It's totally randomly a 3. This is just the problem. It came that way. Okay, so when I fill in this area model, I get, in this first box, I get x squared. Here I have a 2x. Here I have a 2x. And then 2 times 2 makes 4 for this last spot here. So now I can rewrite my equation with all of the stuff inside the boxes added together. So an x squared plus, now I have 2x and 2x, which makes 4x plus 4, that's the constant in there. And this is still all equal to 3, because remember, all I'm doing here is I'm rewriting the original equation. So what I've done so far is I have rewritten this like this. That's all I've done so far. I just multiplied it out so that it was expanded. Okay. Then finally, looking up at standard form at the top, do you see how standard form always has a 0? How it's like always got a 0 right there. So we need this to be a 0, not a 3. So what I'm going to do now is one last adjustment. I'm going to subtract 3 on both sides of my equation so that I get a 0 on the right-hand side. So now what I have is x squared plus 4x plus, and then remember 4 minus 3, that's 1. So we just have a 1 right there. And then this is all equal to 0. And I've done it. This is the standard form of the original equation. So actually, let me just get my colors straight here. We started with perfect square form, and we ended with standard form. So we were able to go in that direction, adjusting our equation. These two equations are totally equivalent. They are equal to each other. They represent the same situation. They're just in a different format. And so what our job today is going to be is to learn how to do this process I just showed you in reverse, where we're going to start with a standard form equation and work our way back into a perfect square equation. All right. Next slide. All right, so continuing with our work on perfect square form versus standard form, the equation x plus 2 squared equals 3 is perfect square form, and x squared plus 4x plus 1 equals 0 is standard form. They are equivalent equations, and equivalent equations have the same solutions. So if we know they're equivalent, I don't have to solve them both. I can just solve the one that I know works. So if we are trying to solve each of these equations, excuse me. So part A, it says, if possible, solve x plus 2 squared equals 3 using square roots. So this is, we're going to go through this process. And then in part B, it says, if possible, solve this equation by factoring or zero product properties. So we're going to try them both. So in part A, I'm going to go ahead and so I don't have to write so much. I'm just going to start by taking the square root up here. I'm just going to square root both sides. And what that gets me is x plus 2. So now I've gotten rid of the exponent is equal to plus or minus the square root of 3. So I'm going to go in and add my notation here because it's not something I know how to type. So plus or minus, boy, I really want it to like look like you can read it. Plus or minus the square root of 3. So that's x plus 2 equals plus or minus the square root of 3. And now I need to get x by itself. So the next step would be to subtract 2 on both sides to get x all alone. And so now we have x by itself here, x equals. And now here's the thing we got to be careful of. -2, we want to combine it with the square root of 3, but the square root of 3 is irrational. It's not a whole number. I can't combine the -3 underneath with things. The root is stuck on it. So what I'm going to do, if I'm not using a decimal, what I'm going to do is just write them side by side for now. So -2, and then I'm going to have a plus or minus symbol, and then root 3. So what my answer will look like is -2 plus or minus the square root of 3. And this technically is the exact solution. It represents 2 solutions. So if we did find this in decimal, we could plug these in. But basically, it represents 2 different solutions. One is when we use the plus, so x equals -2 plus the square root of 3. And one is when we use the minus, so -2 minus the square root of 3. These are our 2 solutions, okay? So if you did want the decimals, you could just punch that in your calculator and that in your calculator separately. All right, so we've got our 2 solutions. Now we go to part B. So we're going to try to factor this. So I'm going to start with my area model. And remember, for factoring, we want this also. And I'm going to plug in my first term, which is x squared. And then I have my last term, 1 goes across from it. And then I need the 2 other squares in my area model to add up to 4x. So that's the bottom of my x over here. But those 2 numbers I choose also have to multiply to be the product of the diagonals that we already know. So x squared times 1. So they have to multiply to be x squared, 2x squared. So now I'm looking for 2 numbers that will do this. And there aren't any. The only way, because remember, there's a 1 right here in front of this x squared. The only way I'm going to get 1x squared is with x times x. And if I put x here and x here, those do not add up to 4x. They multiply to be 1x squared, but they do not add up to be 4x. So we cannot finish this factoring problem. This is not possible. This does not factor. And honestly, that makes perfect sense. Look at the answers. Remember, our 2 equations are equivalent, which means they would have the same answers. How am I going to factor with some weird numbers like -2 plus √3 as my roots or as my zeros? They're irrational numbers. So what I notice is when the solutions are irrational, the standard form can't be factored. Oops, that's supposed to be can't. I don't know where that came from. Okay, here, can't be factored. There we go. All right. Okay. All right, so now we're going to examine how the two different equations we've been working with. So these are not new equations. We know they're equivalent. We know that when we multiply out x plus 2 squared equals 3, we can make it look like x squared plus 4x plus 1 equals 0. Now we're going to start working on how to do the reverse. How do we take the standard form and make it look more like the perfect square form? So we're going to use algebra tiles to model each one. So you can see how in this first diagram, we have x squared, 4 x's. So there's 2 of them here, x, and 2 of them down here, x and x, so that makes 4 of them. And then a 1 square. And then over here, this is x plus 2 squared, and I want to show you why. So just so you understand where this diagram came from. Do you see how the edge of this would be x by x for that x squared, and then this would have a length of 1 and a length of 1 and a length of 1 and a length of 1, which altogether makes 2. So it's x plus 2 on this side and x plus 2 on this side. And then there's these 3 over here, which make this 3 here. So this diagram also fits with that perfect square form. So what we want to do in part A, it says what can be done to the equation on the left, this one, that will result in the equation on the right. So a change in this diagram to force it to look like this diagram. And I see that some people have already answered it on their Pear Deck. Basically, what you would want to see is that we need to add a few more cubes to this diagram to complete the square. And once I've done that, do you see how we just needed 3 more and then it makes this the perfect square like the one on the right? But we can't just put 3 squares on here and like call it a day. We need to make sure that those 3 blocks also get added over on this side as well. So I'm gonna go ahead and draw those 3 blocks over here as well, so that we know that we're keeping things balanced. So essentially, I'm just adding in those 3 blocks on each side. So let's describe that. So the first thing we do is to add 3 on each side. And that gets us a new equation. So x squared plus 4x plus 1 equals 0 was our original. So I'm going to add 3 on both sides of this equation and get our resulting equation, which will look like x squared plus 4x plus, and now we have 3 plus 1 is 4 equals 0 plus 3 is 3. Okay, we're closer, but not quite there yet. Look at this. See, we have here we have x plus 2 squared, and here we have this whole thing. So how do I make x squared plus 4x plus 4 look like that? Look like this expression squared. What should I do next? Because we need those to match. So I can see a couple people writing in, I believe. If you thought that we should factor, you're totally right. We should factor. So what we're going to do is factor. So in order to factor this, we need the edge lengths. And I'm going to redraw them down here, but we do have an area model above we could totally just use. I'm just going to put it down here so you can see it really explicitly. So what we have is all the parts are already done. We know it factors. We know it's a perfect square. So when we fill in our area model, we have x squared. We have 2x here and 2x here. Just like up here, we have 2x here and 2x here on the original diagram. And then we have 4 ones, which we know made it a perfect square. So now the edge lengths are x and 2, just like the second diagram for the perfect square equation. So when we write our answer now, it should look like x plus 2 times x plus 2, which can also be written like this, x plus 2 squared, and that's equal to 3. And we've done it. We have now changed it into perfect square form. I guess I don't have to do that, but all right, so there we go. Okay, so this is part B of the same problem. So we're just continuing thinking about these two diagrams with the area models. So changing a quadratic equation into perfect square form is also known as completing the square. So this is like one of the big goals of today's learning, is that we're able to go from this equation to this equation, like this format to this format. Why is this name appropriate? Why do we call it completing the square? I'll give you a moment. So we just added enough tiles to the diagram to make it a square, which means we added enough numbers, like we added enough units to each side of the equation to make the expression represent a perfect square. So it literally is completing an incomplete square. Or we adjust the standard form expression so that it actually represents the area of a perfect square. Adding the tiles. Okay, so like adding the tiles above. So we just like went in here and looked at this diagram and we're like, oh, we just need 1, 2, 3 more little cubes. And that makes this whole thing a perfect square. That's what we had to do. We're making it into a square, hence completing the square. Okay. All right, so now what we're going to do is practice this, this process of completing the square. And it can look different from method to method. There are a few different methods. One of the methods is to build the thing with algebra tiles. That means take each of these terms apart into sections. So we have x squared right here. We have 6 x's, so we'll put 1, 2, 3 x's here and 1, 2, 3 x's here, so it's balanced. And then we have 5 ones, 1, 2, 3, 4, 5. And then we figure out how many to add in so that this whole thing makes a perfect square. So how do we complete the square? So we want to figure out that empty space there. How many do we need? So if we just like draw in, extend the lines and like this, you can see that we need 1, 2, 3, 4. We need 4 little squares to complete this square. So we're going to also add 4 in over here because we need to be balanced. So if I add 4 on the left, I better add 4 on the right. And what that looks like in our equation then is we just add 4 on both sides of the equation. And that gives us a new equation. So it's x squared plus 6x plus 5 plus 4 is now 9. So now we have a 9 over there instead. Okay. And so here is our new equation. And you can see if we count like each of the squares in our diagram, you can see how we have 1, 2, 3, 4, 5, 6, 7, 8, 9 now to make that perfect square. So you can see it goes with that 9 right there. So there's our 9. Okay, so now we just need to go one step further and put it into perfect square form, because right now we started with standard form. We adjusted the left-hand side to make a square. Now we need to write it as a perfect square set of factors. So what I do is go back to my diagram and I get my edge lengths. So this would be like x here, x by x makes x squared. And then each of these little edges of the longer pieces are 1s. So that's 1, 2, 3. So like there's a 1, there's a 1, and a 1. So I'm just going to all together, that makes 3 for that little portion. There's 3 right here for that little portion. So our factors will look like x plus 3 times x plus 3 equals 4, which we can then write as x plus 3, oops, squared, oh my goodness, equals 4. I'm just going to get my exponent. Okay, so x plus 3 squared equals 4, and now I'm in perfect square form. And at that point, to solve, which it's not asking us to do, but then I'm just going to make a note. So to solve, use square roots. It's not asking us to solve on this, so I'm not actually solving. I'm just making a note that if I was to continue solving and finish the problem, I would use square roots. Now, this second way, notice it's the same exact problem. The second way, what we're going to do is sort of bypass the algebra tiles and go straight to area model, which is going to end up being maybe a little bit easier to create on your own, so you don't have to have those tiles the whole time. Okay, so now we're going to do the same exact problem, just in a slightly different way, okay? So we have this standard form equation. We want it in perfect square form. We already know what the answer is going to look like, but this is a different approach. So what I'm going to do is I am going to fill in the area model in a really specific way. So listen carefully, okay? So first off, this is not factoring the same way that we know about factoring. We're not using the x, it's different. We know exactly that we want this to be a square. We want the sides of this diagram to be the same length as each other. We're trying to complete the square. So what I do is I start with x squared, since I know that is a square. So that's going in. X squared goes into the first box just like normal. It's a square, so that's a good start. Then, in order to make this a symmetrical, like two sides the same length as each other thing, what I'm going to do next is I'm going to take the middle term of my original equation, the 6x, and I'm going to cut it exactly in half. And I'm going to put half of it here and half of it here. And don't fill in the last square yet. So because I did that, what I ensured what I ensured about this diagram is that this side, now that I highlighted in green, will be the same as this side. And before we even fill in that last square, I'm going to get the edge lengths right now of my square because I have made a square, almost done. And then I'll finish it in a second. So we know x times x makes x squared. And then x times 3 makes 3x. And x times 3 makes 3x. And see how you can see now the edges are x plus 3 and x plus 3. We know our factors now. They are identical. But we need to make sure that the number we have on the other side that's replacing the 0 makes, if everything's balanced out, to be a square. So now I look for my last square, my last section of my area model. Do you see how I have a 3 here and a 3 here, and 3 times 3 would actually mean that this spot needs to be a 9. So what that means for my equation is that I need that number to be a 9. So I have to think about what can I do to the 5 to turn it into a 9? And that would be to add 4. So if I add 4 on both sides, I now am ensuring that I have a 9. And now I'm going to rewrite my equation. I have x squared plus 6x plus 9 equals 4. I've done it. Do you see how now this part of my equation represents all the stuff inside of my area model? X squared, 3x and 3x makes 6x, and there's a 9. We have completed the square. And the only thing left to do in order to get it into perfect square form is to write out the factors of x squared plus 6x plus 9, which are the ones in green on our diagram. So finally, I write this as x plus 3 times x plus 3, which I'm just going to skip that step and write x plus 3 equals 4. I'm going to put a square. So x plus 3 squared equals 4. And we've done it. So this is a little bit different than the area model in that the parts of like the steps, the stages we did was we took x squared and we put it in the bottom corner of the area model. We cut the middle term in half and put half of it here and half of it here. And then we got the edges of our square first to determine what number we would need that would complete the square. And then we added in the difference to make it happen in our equation and worked it out the same at that point. Okay, now I'm going to clear and we're going to do one last method. So there's one more method I want to show you, and it has to do with an algebra sort of process. So here we're completing the square with algebra. Again, it's the same problem. So this helps to like make it be, it's a little more abstract, but once you start seeing this pattern, it will save you all the extra drawings. Okay, so some people will feel ready for this and some people won't, and that's okay. There's no reason you can't use the area model all the time. So the second method, the one we just did, you could use all the time. You don't have to do this. But here's how this goes. So first of all, we're in standard form. Excuse me. Step 1 says if a does not equal 1, so see in standard form this a right here, if that a is something other than a 1, we need to divide the quadratic by a. But in this equation, a is 1, so we don't have to worry about it. So that is done. That is taken care of. All right, so we already have a is 1. Step 2 says write the quadratic in the form x squared plus bx equals c. So now what we're going to do is we are going to subtract 5 on both sides of this equation. And what that's going to do is get us a new equation. Here, I want you to be careful before you write it all out. I'm going to put x squared, and then I have plus 6x. And then I'm actually going to add a blank. I'm going to put a blank here. And that's where I'm going to add in the number that I want. So you got to leave a blank on both sides. So here I have x squared plus 6x. I just subtracted the 5. So now the -5 is over on the right. And I need to figure out what to put in that blank so that I have a perfect square on the left-hand side. So we know from our previous problems with the same equation that the missing number would be a 9. But how we find that algebraically is with this little formula. We take b from standard form, that's the second term. This is the 6 in this step here. The 6 is our b. We divide it in half, and then we square it. And this tells us what number to add. So what I'm going to do is I'm going to take that, I'm going to take that 6. I'm going to change my color. I'm going to take that 6. I'm going to divide it by 2. And then I'm going to square it. So that would be a 3 squared, and 3 squared is 9. And just remember, you have to add that same number on both sides. So if I take the second number and cut it in half and then square it, it's 9. And just to remind you what it looked like, remember our area model from before? We had, you don't need to write this, I'm just going to show you here. We had like x squared in here. And then I took the middle term, 6x, and I cut it in half, 3x here and 3x here. And then that made our edges x plus 3 and x plus 3. And then the missing number was 9. Essentially, what I'm doing is cutting this number in half to get our 3's, and then 3 times 3 to get our 9. So it's kind of the same thing, it's just all numbers. So now what I've done once I added that 9 is I've gotten myself my new equation that looks like this. X squared plus 6x plus 9 equals -5 plus 9 is 4. And this is what we did in each of those previous slides. We got this equation. And at this point, now we need to figure out how to write it in perfect square form, like with the factors. So you could go through the whole factoring process, but I want to remind you that this is actually representing a perfect square. We chose this 9 on purpose so that it was a perfect square, which means we know that this is going to factor, like x plus or minus something squared, and then equals 4. And now we just need to figure out what goes in that spot. And the number that goes in that spot shows up in multiple places in this problem, okay? When I took this 6 and I cut it in half and got a 3, that it showed up there. When I when I squared that number and turned it into a 9, the square root of that is also the number. So all I have to do is look at this number and take half of it, and that's the number that goes into our factor. It's this 3. It's half of the middle term. It is the b over 2 in the b over 2 squared. So I'm going to go ahead and get my typing again. So I'm just going to plug in now a plus 3 inside my parentheses. If that feels uncomfortable to you, you could always just do a factoring of this expression, but it will come out as a perfect square if you added in the correct number. All right, so we had a 1 in front, so we didn't have to divide out the a. We subtracted 5 on both sides and left a blank, so now we had taken care of step 2 and left space for the number we really want that completes the square. And then we used our b over 2 squared and added that in on both sides, which was our 9, in order to get our perfect square form. And then we factored the left-hand side. Boom. And now we have factored form. Okay, so now I just want to remind you that some of our equations that we solve will have two solutions. So, and that means we'll have like a plus or minus in our answer or two whole numbers that come out. Some of our equations will only have one solution where we have one x-intercept, and some will have no real solutions because the parabola doesn't even reach the x-axis. All right, so we're going to go through several of these types of problems. And this first one, I want to give you a few minutes to try to do on your own, and then we'll walk through it together to make sure that we have it down. Okay, so I'm going to give you a few minutes to try. Okay, just to get you started here, if you say you were using the area model method approach, you start by building your square. And this one I just want to clarify. So when you fill in the numbers from your equation, remember the 7 isn't what we want it to be. So we're going to leave the 7 out right now. And we're just going to put our x squared, because that's a perfect square. We're going to cut our middle term in half. Negative 6x divided by 2. If we cut that in half, that means we're going to have negative 3x here. And negative 3x here. And then you want to get the edge lengths in order to decide what goes in the fourth section. Okay, so just to continue where I left off, so we have x squared here, and in order to get x squared, we would just multiply like x times x, and then x times negative 3 makes negative 3x, and x times negative 3 makes negative 3x. Remember, we need these two edges to be identical. So if your numbers are not exactly the same, if you don't have x and minus 3 and x and minus 3, something is off, okay? And then that last space, negative 3 times negative 3 makes that last space, which means this would have to be a positive 9. And that tells me that I need to adjust my equation so that instead of a 7, I have a 9. So I would add 2 on both sides to force it to be a 9. And now I have x squared minus 6x plus 9 equals 2. And then I can just factor this because I have my factors already in my diagram on the edges. This is x minus 3 squared equals 2. And then finally, it's saying, please solve your equation, solve it all the way. I want to know all my solutions, however many I have. So I'm going to square root both sides. And I'm going to add 3 on both sides to get x by itself. And this gets me x equals positive 3 plus or minus the square root of 2. And I'm going to leave it like this because, I don't know, this is a perfect answer. This is just fine. It's the exact answer. It has an irrational root 2 in it. That's fine. I actually have 2 solutions here. So there are 2 solutions in this. I have 3 plus root 2, and I have 3 minus root 2. So I'm resuming recording. So what I'm going to do is see if we have, see what we have here in our area model. So when I build this thing, let me fill this in. All right, so I have p's instead of x's, but it's the same idea. So I have p squared here. I'm going to cut this middle term in half. So I cut in half the 2p. 2p in half is just 1p. So 1p plus 1p. And then my edges would be p times p is p squared, and p times 1 makes p. So 1 times 1 would be 1. And look, we already have a 1. We already have it. This is a perfect square already. That was nice. So now I'm just going to go ahead and write this as p plus 1 squared equals 0. And I'm ready to solve. So I'm going to go ahead and square root both sides. P plus 1 equals plus or minus 0, which is just 0. Subtract 1 on both sides, and it looks like p equals -1. I have one solution to this problem. One solution. So if you already have a perfect square, so that you don't have anything other than 0 on the right-hand side, then it's going to end up being one solution, one answer. And so that's like a nicer, quicker problem. If you used the other method, you would find it works out just fine, because if you subtract the 1 over, you find you have to add in a 1, you add a 1, you end up with 0 again anyway. It totally works out just fine. Okay, next, here I go. All right, so for this one, I'm going to go ahead and start the same way. You know what? I'm going to use the algebra method. Okay, so I'm going to subtract 9 on both sides. So I have k squared minus 4k, leave a bunch of space, equal to -9. So I'm going to just like leave spaces here and here. Now I'm going to take this -4 and divide it by 2 and then square it. Because remember, we're going b over 2 squared is our little formula. So this gets me -2 over, -4 over 2 is -2. So -2 squared is plus 4. So I'm adding 4 on both sides of this. So now I have the equation k squared minus 4k plus 4 equals -5. All right, continue up here. So I need to factor this, and I know I made a perfect square. And so remember this number inside -2, or half of the middle term, -4 is our inside number. So I'm going to have k minus 2 squared is -5. And at this point, I can see that I won't be able to solve, because taking the square root of a negative is a no-no. So this would be no real solutions for this one. No real solutions. So if you end up rewriting it in perfect square form and the right-hand side is a negative, you can stop right there at this point. We will learn how to deal with this in a couple days, but like right now, we don't know how to do that yet. All right. I have 2 more little things I want to show you. So in this one, there's a slightly different weird thing when the second term is odd. So you see how we have a 5 here? Things get a little weird because the numbers are decimals. So I want to show you how to deal with this. Okay, so I'm going to start with my area model. And I fill in my first term. So I have an x squared here. And then remember how I fill in the next 2 boxes? I take half of the middle term. Well, 5 divided by 2 is 2.5. So I'm actually going to have a 2.5x here and a 2.5x here, and I'm allowed to do that. So when I write my edges, I have plus 2.5 and plus 2.5. Weird, I know, but it's fine. And you use a calculator, and 2.5 times 2.5 is 6.25. So what I want is to change my 4 to a 6.25, which means I'm going to add 2.25 to both sides of my equation. So now I'll have x squared plus 5x plus 6.25, because there's my square, that's from my diagram, is equal to 2.25. It's not pretty, but there it is. And then remember the factors, I know it's a square, so I'm just gonna go ahead and do this and fill in my, I know it's an x, and then I need half of the middle term, half of 5, which is 2.5. It's also from my diagram on the right. And then to solve this, square root both sides. And I get x plus 2.5 is equal to plus or minus, and this is interesting, it comes out as 1.5, which in the end, I actually get whole numbers. This is kind of interesting. What I get is x equals negative 2.5 plus or minus 1.5. And when I use the plus, I get x equals negative 2.5 plus 1.5 is negative 1. And when I use the minus, negative 2.5 minus 1.5, I get negative 4. Two nice whole numbers. Strange. Okay. I know we're out of time here. One last one before you go. I'm so sorry. I'm not going to finish this. I'm just going to start it for you just so that you see it, okay? So I want to point out that in this one, our leading coefficient is not 1. Do you see how there's a 2 here? So what we would have to do first is divide every term by 2. And then get our new equation. And then complete the square, okay? So now you would continue from there. All right. All right, so to finish this, we need let's do our area model, or let's do our equation style one. How about? All right, so I'm gonna add 3 on, oh, that didn't work out as planned. Okay, so I'm gonna add 3 on both sides. So now I have x squared minus 4x with some space equal to 3. I'm going to take half of negative 4 and square it. So that gives me negative 2 squared, which means I need to add 4. So now I have x squared minus 4x plus 4 is equal to 7. And I know this is a perfect square because I followed the perfect square pattern. So now remember we have our x here, so that's our first part. And then I just need half of the middle term, so minus 2 instead of negative 4, just take half of the middle term. And now I'm going to take the square root of both sides. And finally, add 2 to get x by itself. And because that root 7 is there being all irrational, I'm just going to leave my answer in exact form like this. I can't combine root 7 and 2, so I just put them side by side. And I just, make sure I understand that this is 2 plus root 7 and 2 minus root 7. I have 2 solutions. And that is it.